and welcome to Chapter 5 of the Joy of Abstraction book club. Thanks for being here, and thank you to the Topos Institute for hosting this book club. There are some really great questions again this week. Sorry, I didn't mean to sound surprised. I'm just enthusiastic. And I'm also keeping myself lively because I'm quite tired, honestly. It's a bit late this evening. My day got away with me, but I really wanted to get this video made today. I did have a complete catastrophe in the kitchen this morning, so that definitely wiped me out a little bit today. Yes, it involved a broken jar containing almost a liter of, well, soy sauce braising liquid. That is not something I recommend spontaneously exploding all over your kitchen. And it was amazing because it looked like there had been a massacre of someone whose innards, the blood was made of soy sauce, and it splattered on the inside of cupboards where the doors were closed. I thought I'd got everything, and then later in the day I opened a cupboard and there it was, splattered, dried up. It was terrible. Anyway, I don't recommend doing that. Chapter 5, here we are. Chapter 5 is about relationships, and we're getting into some meaty stuff now. So here are the first questions. There are, I will say, just to give you a heads up, there are quite a few from people who've seen some more things in category theory than I'm expecting at this point. So hope you won't feel put off if there are some things that you have no idea what they're talking about. But I'd like to answer all the questions. First question, I've seen the squares used in category theory, the commutative diagrams. Is there an important sense in which these are symmetric? Well, the usual form of a commutative square in category theory, well, let me just try sharing the whiteboard screen. Okay, so the usual commutative square shape is like this, with two arrows going down the left and the bottom, and two arrows going down the right, the top and the right. And so there is some symmetry involved there, because there's a line of symmetry going down the diagonal here, but not the other way. Now, I'm not sure if that's quite what you mean, but that's what I can think of as a kind of symmetry at the moment. Okay, let me come back to the full screen. The next question is, this book covers a lot of concepts from family structure to lattices of factors to income inequality. I've heard the phrase, all concepts are Khan extensions. Yes, that's one of the phrases from, I think it is in Categories for the Working Mathematician. I don't know if McLean said it before that. But is there any sense in which we're examining Khan extensions, or am I totally off base? Well, I mean, seeing as all concepts are Khan extensions, then yes, all of these things are Khan extensions. Whether they are all Khan extensions in a illuminating way is a whole nother question, right? And okay, here's a secret. I'm not really that into the slogan, all concepts are Khan extensions. Now, of course, you may not know what a Khan extension is, and sometimes I think I don't really know what a Khan extension is myself. Maybe I don't like the slogan because I don't feel that good at Khan extensions compared with some other things I'm quite good at. But I also think that one of the reasons I'm not that good at Khan extensions is that they don't really fit much of my intuition about what things are. And the thing is that a Khan extension is a kind of universal property. Some people say it's the most universal kind of universal property, but I think it's just a kind of universal property. A Khan extension is also a kind of a junction, and a junction can be defined as a kind of initial object. An initial object is a kind of limit. Limits are all a kind of an adjunction, which are a sort of Khan extension. So they're all really the same thing. It depends what your point of view is. I am more likely to think that all concepts are initial objects, honestly. And the thing is that concept in that doesn't really mean thing. It really means construction. And so a lot of the things that are examples that you mentioned in this list, in this question, they're really examples of structures, of constructions, rather than constructions themselves. And so I wouldn't have said that every object is a Khan extension. It's like, this is my hand. Is it a Khan extension? Well, yes, I could probably fabricate some sense in which it's a Khan extension, but would it be illuminating? That I'm not sure about. So Khan extensions, well, they're about extending things. They're about knowing something here and then saying, okay, I know something in a restricted situation. Can I expand my knowledge to something else? So I suppose anytime you think you're expanding a construction from a smaller context to maybe a bigger one, then that's sort of what is going on with a Khan extension. But again, if you don't know what Khan extensions are, and that made no sense, then I admit I'm not even going to get to Khan extensions in this book. But my aim with the category theory content in the book was to get to a point where you know enough of the basic stuff that you can then go and read a textbook that introduces those things. Okay, next question. The last sentence before section 5.2 on symmetry. So I will say that there are many different uses of the word symmetry floating around in this chapter. So I had to look this up to make sure I've got the right one. Alludes to a way, so this is about relations when we're talking about reflexivity, symmetry, and transitivity. And I was talking about relations going backwards. And it's alluding to a way of imposing conditions in order to avoid ambiguities. So this question is about clarifying what I mean as the source of and solution to this apparent ambiguity. So section 5.2, do you know, I think this question isn't quite necessarily in order, but I'll answer it now. Anyway, section 5.2, right, just before it, I've got these two examples where there's some ambiguity in what's going on. So, you know, while I've got this whiteboard thing open, let me share that again. Right, so the idea is that if A is the mother of B and B is the child of C, then there's some ambiguity here, because it's not clear if A and C are the same person, right? It's possible that B could be the child of C and C is the father, or that C is the other mother. And what this is saying is that there is not a uniquely knowable relationship from A and C given this information in front of us. And so when I say that we're going to see a way of we're imposing some conditions to eliminate those ambiguities, what I mean is not that I've got a way of eliminating the ambiguity in this situation. What I mean is we impose some conditions so that this situation doesn't count as something we can do in our framework. Because what the condition is going to be for a category is that whenever you have a known arrow from A to B and a known arrow from B to C, you know that there is a way of getting from A to C. And you know exactly what I mean is you know what the result is. You know exactly how to get from A to C. It is uniquely specified and there isn't any ambiguity. If you want to encode a situation that does have some ambiguity, you have to go a bit higher dimensional and say that there exists a relationship, and then you have to specify what counts as a valid version from A to C. So in this case, you might have to say there is a relationship from A to C. We're not sure what it is, but we know that there is one. And then that gets us into situations that we might call non-algebraic, where we know that the composite exists, but we maybe can't specify it unambiguously. So that's what I mean by that. What is the source of this apparent ambiguity? I suppose the source is that there are, in this case, it's that there are too many things going on. It's the fact that child of B is the child of various different people, and so perhaps that's what it is. Or yeah, I'm not sure if that really fully answers the question. What is the source of that ambiguity? That's a very interesting question. In fact, I'm going to pause and I'm going to stop this share and just pause for a second to see if I can think of something more illuminating to say about that. Okay, I've thought of something a little bit. I'm going to share that screen again. I think it's something to do with the fact that B is the child of two people, C and D. And so that's sort of the same type of relationship. But when you compose this relationship, the relationship from A to C is not the same as the relationship from A to D. And so we don't know from just this statement, we don't know which one of these it is that we've got. I think that is what it is. I think to make this situation more precise, because I haven't really set this situation up in a precise way at the moment, if I were going to, I think what I would say is that actually here, there is a specifically known, there is a specified relationship from A to C in this family. We just don't know what it is. And that's different from there not being a specified relationship. So I think that's a slightly profound point. I think I'm in danger of complicating, or as I sometimes like to say, complicating the issue by saying any more than that. But the key point is that, let me just stop this share again. The key point to take away from that is that when we make the definition of a category, we're going to insist that given an arrow from A to B and an arrow from B to C, there is a unique determined composite of those two arrows so that we get something from A to C and we know exactly what it is. And that's how we eliminate that ambiguity. Okay, so the next question. When I finished the chapter, I tried to make a diagram with arrows to depict distance as a relationship between locations. Is there a simple way to draw it that somehow captures the differences between the taxi cab distance and the crow distance? So that's a really interesting point, because when you express a space with distance as a category, any valid type of distance will do. And so in a way, the category structure can't exactly tell those types of distance apart. And that's kind of the point, that once you're looking at the structure, the category structure, it doesn't matter what has given rise to that category structure. All that matters is what the structure is. And so if you care whether the distance from A to B is bigger than the distance from A to C, and that maybe in one case, in one context, it's bigger and in another context it's smaller, then you need to know something more than just a category in order to make that comparison, because you need to know that there is a concept of size on the things you've got as your arrows. So if you just have arrows and you happen to label them with things like 3 and 7, then the basic concept of a category isn't going to know that 7 is bigger than 3. And that's where enriched categories come in, where we have more than just arrows with labels on them. We have arrows with some structure on the arrows themselves so that we can say more about what those arrows mean. And I think that may be why you couldn't find an illuminating way to draw that diagram in a way that would make the difference between those types of distances clear. So someone else said, is there anything you would have liked to include in this chapter that was left out, either for lack of space or because it was in the gray area, the boundary of the scope of this chapter? That's a really interesting question. And you know, I can't for the life of me remember. was when I was writing this, I was very clear that there was going to be a space limitation. And so I was really trying to be kind of minimal the first time I wrote it. It still came in like 100 and 200 pages longer than I originally said. I think I originally said I was going to make it 300 pages, and it's come in at 420 or something. And my first draft was something like 550. And I did make it a lot shorter by doing spectacularly complicated typesetting in order to make the diagrams embed into the text. That's why the diagrams are never by themselves in the center of the page with no text at the side, because I was trying to fit it into a small number of pages, which seems an odd thing to do in this day and age, but it is a book, and I did want it to be a physical book. So I tried to make it shorter, and then I asked if I could please make it 420 pages, which I thought I didn't want to make it shorter by taking out exposition and explanation, because I wanted it to be chatty, and I didn't want to take out content because it already feels like the bare minimum of basic category theory content. And so I just didn't want to I thought it would be a less helpful book if I made it shorter, and that it's not a daunting 420 pages, because the reason it's 420 is that it's chatty and got explanation. So I hope that's how it feels. And I did pick up Tom Leinster's book, the Category Theory Operas book, just to see how many pages it was. And on the day I picked it up, it was exactly the same number of pages as my PDF. And so I took that as a sign. Right, so back to the questions. Page 52, second paragraph. Someone says, we could consider taxicab relationship as a setting, and is this setting the context? So in the second paragraph, what I say is that distance can be viewed as a relationship between locations, and there are also other possibilities of what the contexts are. So what I really mean there is the context isn't what gives you stuff that you aren't allowed to physically move. It tells us what we're trying to measure. And so if we're taking one-way streets into account, it's not that anything has physically moved, it's that we're measuring a different way of moving ourselves around between place to place. And so walking distance is a different kind of way of measuring, but it's also, well, because cars can go in different places from humans on foot. And there might be pedestrian walkways or staircases that cars can't go up, or pedestrian streets. But then we could also do something like measure the time it takes to get somewhere instead. Just like when you use Google Maps to get the directions from A to B, if it's taking traffic into account, it may give you the shortest route by time rather than by distance, because it's measuring things by time rather than distance, which is a different setting. And so again, it's not that anything has physically moved in space, it's that we're considering different criteria for what the relationship is between those places. Okay, page 54 is that there's another question about symmetry, but this is really sort of rotations and reflections and things. So the question is, it looks like symmetry is the study of particular invariances. Can the concept of symmetry be extended to study invariances in general? The answer is yes, and that's kind of what group theory does. It's sort of what Galois theory is about, because Galois theory is about things staying the same when you switch the variables in an equation. And it's what's the question again? Symmetry extended to study invariances in general. It's what Noether's theorem is about in physics, really. I think that Noether's theorem says that all conservation in physics comes from invariance in the mathematical situation. And to find invariance, you look for symmetry in a situation, and that gives you an invariance. And so when you look at, if you look at, say, the rotational symmetry in a physical system, because there's no, when you look at the rotations in a physical system, there's no sort of concept of 0 degrees. You have to just pick a reference point. And so if you rotated it, everything should, there should be a symmetry in what you're seeing in the physical system. And that gives us an invariance. The invariance is angular momentum. And so that symmetry in the system gives rise to the invariance of angular momentum, which is the conservation of angular momentum. So I'm not sure if that's what you're asking. I am sure that that was not the greatest ever explanation of Noether's theorem. I'm not a physicist, but if you look that up, you'll see. And I think it's fascinating to think about how those symmetries lead to those invariants. So another one is symmetry under, gosh, am I going to get this right? There's symmetry under translation. And I think that just gives us conservation of, and maybe it's time. Symmetry under time gives us conservation of energy. Okay, I'm going to pause the video and just think slightly harder before I continue. Okay, yes, it's definitely one of those step away from the whiteboard to figure things out. Translational symmetry gives rise to conservation of ordinary momentum. Rotational symmetry is the invariance of angular momentum, and symmetry across time is conservation of energy. That's invariance of energy, total energy of the system. Page 57, how could non-associative multiplication rules be described whilst still using maps which are themselves associative? So page 57, what am I talking about on page 57? Oh, I'm talking about maps for addition. So I'm drawing diagrams where I've got one map saying something like +1 and another map saying +2 and giving +2. So whoever asked this question knows something about the fact that associativity of composition of maps is going to come in. I haven't said it in the book, so if you aren't aware of that, then that's fair, because I haven't said it yet. But since the question has been asked, I will just say that the composition of maps in a category is going to be required to be associative. And so indeed, it cannot model a process which is not associative. And that's one of the reasons that we have higher dimensional categories, because there are things that we want to model that are not associative. And we have to go into higher dimensions to model it in order to get ourselves a situation which is not required to be associative. And the reason we go into higher dimensions is that in a one-dimensional category, arrows are only the same or they're not the same. There's no in between. And so if something is just totally not associative at all, then we might not want to have any relationship between the two associations of arrow. But many of the situations we're interested in aren't just catastrophically not associative. They're somewhere in between. So the two different associations aren't completely different, but they're just not quite the same. And so in order to say that those things are not totally different, but not totally the same, we need a relationship between arrows. And so that's where higher dimensional categories come in. The next question is about the bottom of page 58. Generalizing the situation of the diagram at the very bottom of the page, the special case situation, is the very first thing to the left, the source of all the first arrows, the specialist case of something. Does that have a relationship to the notion of initial objects? Yes, it does. Yes, it can be one. So if you don't know what an initial object is, then that's fair, because I haven't mentioned it yet. But if you do, then you've correctly spotted that that is an initial object. Yay! Okay, page 59. I write that a kite has adjacent pairs of edges the same and only one pair of opposite angles the same. Thank you. That is a typo. It's a kind of a braino. I mean, it's a kind of I didn't state this very clearly. So I've now put a correction on the errata page, because what I mean is that a kite is required to have adjacent pairs of edges the same, and it's required to have one pair of opposite angles the same. It is allowed to have more than that, but that is what is required. It is only required to have one pair the same. Good. Page 60. In this chapter, we're studying squares and then lattices of factors, which look like a structure built of squares. Yes, they are a structure built of squares. That's excellent. We will come back to that when we talk about product structures, because we'll see that those lattices are categories built from square categories, just like physical cubes can be built from physical squares. What is the significance of symmetry in a lattice? Is there anything useful we can learn by rotating lattices? Why, yes, there is. Thank you for asking. Let me go back to this whiteboard where we have to think about the symmetry in a particular way. So in the lattice that I drew on that page, what we have is 30 at the top, and then we have 6, 10, and 15, and we have 2, 3, and 5, and 1 at the bottom. And I think my arrows were going up, 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 up. And so what we have to do geometrically is think about the symmetry of this cube standing on the vertex given by the number 1. And if you do that, then what you see is that the 3 middle vertices, what am I trying to do? I'm trying to change color. The 3 middle vertices rotate. So if you rotate it standing on 1, then these 3 vertices are on the same level and will rotate among each other. And these 3 vertices will also commute among each other. And what this is telling us is that the numbers 2, 3, and 5 are playing the same role inside that category. So as a cube, this thing has more symmetry than it does as a category. So as a cube, for example, it has symmetry along vertical planes that as a category it doesn't have. As a category, what we've got is a symmetry through the middle rotationally, where 2, 3, and 5 play exactly the same role as each other, and 6, 10, and 15 play exactly the same role as each other as well. And for the number, what that's saying is that 2, 3, and 5 are the prime factors. And that because this diagram is only talking about factors and it's not talking about size, 2, 3, and 5 are not really distinguishable from each other as factors of 30. We can only distinguish them from each other by knowing what size they are. But we're not talking about size, so we don't know that. If we then look at the further abstraction on page 64, then what we do is that we replace it. Oops, that's not what I meant to do at all. What we're doing is we're looking at the factors at each vertex, and we're saying we replace 30 by its prime factors 2, 3, and 5, and then we say, oh, well, that could have been just any 3 things, A, B, and C, and then here we have the 2 element subsets, A, B, A, C, and B, C, and then we have the 1 element subsets A, B, and C, and then we have the empty set, but we have the same arrow structure. And if we look at it now it's perhaps even clearer that there is a symmetry between the roles of A, B, and C, because A, B, and C are just 3 things. We can't tell them apart at all. And so the rotational symmetry standing on what's now the empty set is telling us that we really can't tell the difference between A, B, and C, so we can rotate them on top of each other in any way we want. Whereas in the diagram of factors of 24, there isn't that symmetry. So 2 and 3 are really not playing the same role in the diagram of factors of 24. And so, yes, that is what the symmetry is saying. And later on, when we talk about this as products, we'll see that this is a product of, there's a category that we could call I for interval, and it's just got 2 objects and an arrow. And that what we're doing is we're taking I times I times I to make this cube, which is like taking the product of 3 intervals to make a cube. And because inside this expression, we really can't tell the difference between I, and that's where the symmetry of the situation is coming from. Very good. So related to that, someone says that they somehow feel the notion of dimension should be generalized to refer to the number of non-unique prime factors. So for example, 24 should have 4 dimensions, but in a degenerate way. Is there some sense behind this intuition? So I think, yes, there is. I think there is generally sense behind all intuition. We just have to figure out what it is. And in this case, I would say that, okay, here's the diagram for 24. So we have 24 at the top. We have 12 and 12. Wait, what am I talking about? What am I talking about? I prefer doing it from the bottom. We have 2, 4, and 8. And then this direction is multiplication by 3. So we have 12, 6, and 3. So these 2 have very different shapes, but they both have 8 factors. And what we can say, what we can do is, so this person's saying it should have 2 times, this should have 4 dimensions, because 24 is 2 times 2 times 2 times 3. So as a sort of physical shape, it's only got 2 dimensions because there are only 2 distinct prime factors. But what we can say about it having 4 factors is that the longest possible path that you can take through this has length 4. And so there are various ways to get to 24, but all of them will have, every path will have length 4. In this diagram for 30, the longest possible path you can take is length 3, and also the number of dimensions is 3. And so, very good. Here's something I haven't thought of before. Thank you for this question. We can think about the relationship between the number of dimensions of the physical diagram and the maximal length of path that you can take. And some things I can think of immediately are that you can take, there may be no restriction because you can go any number of times you want in a straight line. So you can have a maximal path of length n all in a straight line. So you can have a one-dimensional thing with a maximal path of length n. Then I wonder if you can do everything in between. Well, that's a nice thing to think about. So thank you very much for that question. Someone says, is there something like a basic building blocks concept in category theory, like things that can't be broken down further that we can combine to build larger things? So this person knows some things about category theory already, so don't panic too much, or as I like to say, just panic exactly the right amount if you don't know these things. So they're talking about prime numbers, irreducible representations in group theory, generating vectors in an exterior algebra, for example. It's a very good question. So anytime you see something that looks sort of feels similar in different branches of math, then the question will be, can that be done in category theory? And the question is, how much structure do you need in your category to be able to express that? Because sometimes things happen because there's a little bit more structure and you can't do it just in any old category. And so for this one, the first thing that came to my mind is something to do with categories that are constructed to be reminiscent of the category of abelian groups. So basic categories are often, some categories are constructed to be reminiscent of the category of sets, and others are reminiscent of the category of abelian groups. And in the category of abelian groups, certain things happen, such as the 0 is the same as 1. So the yeah, I'm jumping ahead now, but basically the terminal object is the same as the initial object, because you can't have an empty group. A group has to have at least an identity in it. So the smallest possible group is the trivial group that contains exactly one element, which is therefore by necessity the identity. And so that's kind of the 0 group, and it's also 1, and so 0 equals 1. So that's something that happens in the category of abelian groups. So when we're trying to make things happen in a general category, we go, well, what was it in that world that made these things possible? And the concept of an abelian category is kind of a place that's constructed to be where you can do the sorts of things you can do with abelian groups. And there is a concept called simple object in an abelian category, which is kind of that, and I believe it gives irreducible representations if you put yourself in the right kind of context. For prime numbers, I'm not so sure. I will think about that. Number theory is something that I think of as still being quite remote from category theory in certain ways. And maybe that's it, because there isn't structure, which is funny because numbers have a lot of structure, but there isn't this kind of structure floating around. I now feel the need to Google something about prime numbers and category theory, which of course everyone can do together. So I'm going to press pause now, and you can all press pause too, and also Google prime numbers and category. Okay, my brief Google search there did not yield anything particularly interesting, other than a reminder that in number theory, the way we think about prime numbers as not being able to be factored into smaller things is really the definition of an irreducible. And I think that that's why it's in this list with irreducible representations. And so if we look at the category of natural numbers where the arrows are given by factors, then the irreducible elements are the ones that kind of only have an arrow from 1. That's it. And the definition of prime in general is a bit more convoluted than that and sounds even less categorical than that. But supposing we're talking about irreducibles, then I suppose that would be the definition, that it's kind of one step away from being initial. And I don't know, that's kind of interesting. I haven't thought about that. So thank you for that question. That's another interesting thing to think about. I think that is all the questions. So there's just some appreciative comments at the end. So thank you for those appreciative comments. They do really help me. I like them. So someone said, thank you for speaking up about social justice issues. Gosh, well, thank you for thanking me for speaking up about social justice issues, because there are, as you say, I know you must get pushback about it. Yes, I get lots of pushback, anger, people get mad at me. Sometimes they heckle me during my talks. So it is kind of unpleasant. And I sometimes sit there and go, oh my goodness, why do I put myself through this? Why? It just causes me so much pain. And then I think, I'm doing it because I care about those issues. And although it does cause me pain when people get angry with me, it would cause me more and worse pain for me to sit around not doing anything about it, honestly. Someone says, please keep going. We will be here to the end. Yay! So we have a few months to think about what to do as a celebration at the end. I don't know. Thank you, Dr. Chen, for being kind, encouraging, and making the context of the book club feel like a friendly discussion. Oh, that's nice. I'm so glad. Now that we're starting to get into more complicated things, it's definitely, I mean, it gets harder and harder as it goes along, right? I liked how Dr. Cheng mentioned breaking her own rules about thanking people as a transition into thanking people. Oh, thanks. felt like it was a demonstration of how to use rules to help guide towards including something important instead of as a judgment for punitive consequences. That's a really good point. So I would say that that's a congressive use of rules in a way. And I suppose it would be more congressive to call it guidelines rather than rules. And I do find that guidelines, when they're done well, it's like politeness and manners and etiquette. It's there to help us, it should be there to help us have a society that runs smoothly. And so I have rules like that that are guidelines or things like a checklist to help me remember to be nice actively rather than just thinking it silently inside, because I like to think that even if I'm not actively thanking people out loud, I'm feeling grateful towards them. I just need to remember to vocalize it. Thanks a lot. The book club is going great. Oh, I'm so glad. It's really nice to hear that. I'm really enjoying it. Thank you so much. I've been really enjoying this book club. Well, thank you. I'm really enjoying it as well. And so I'm glad to know that you are, because it would be really sad if I was just sitting here enjoying it all by myself and no one else was enjoying it. So thanks for joining us, and thanks for your questions. It's really interesting. And I always say one of the reasons I love teaching is because I learn so much from it. And so answering your questions has given me loads of things to think about. So thank you very much. Please keep the questions coming, and I really hope to continue helping you to understand more things about category theory. All right, thanks. Bye.